We're going to leave algebra for now. Well, we're still going to use it, of course. Let's go into the area of probability. Okay, probability, which actually is part of statistics, is probability. So, some definitions to begin with. Probability is a good definition to start off with. The chance of something happening. Now, there are different types of probability. Experimental probability, also known as relative frequency, and that's when you base the probabilities upon actual data that you collect. Okay, so we toss 5 coins and they end up landing head, head, tails, tails, and heads. So the experimental probability of tossing a head would be 3 in 5. From our data, we'd say, oh, okay, well, there's 3 chances in 5 of getting ahead. Now, the theoretical probability is actually a half. So that's the difference between the two. So experimental probability is when you've conducted some sort of experiment, you've gathered data, and from that data you make a conclusion about the probability, as opposed to the theoretical one. Okay. Now, what should happen is as you repeat the events, well, an infinite number of times, if that is possible, then the experimental probability should approach the theoretical probability. So theoretical probability is what we would expect to happen if we could do it an infinite number of times. It would work out. Sample space is every possible outcome that we could have. So with that tossing of a coin, there's only 2 outcomes. You get a head or a tail. Event space is all possible ways a particular event can occur. Equally likely events, as the name suggests, events that have the same chance or equal chance of happening. Then we have these things called mutually exclusive events. So only one possible outcome could occur at any one time. So an example, back to our coin again, when we toss a coin, it could be a head, it could be a tail, but it could not be both at the same time. So they would be mutually exclusive events, which then talks about non-mutually exclusive events, and they are ones which could happen at the same time. My example of that is a number. Well, it could be even. It could also be a multiple of 3. These are 2 different things, but they could happen at the same time. It is possible to pick a number that would satisfy both of those. So they would be non-mutually exclusive events. Okay. Notation we use in probability. So P for probability, and then in the parentheses, whatever event it is we're talking about. So I've just put E there for some event. And that just means the probability of E happening. The complementary events, the probability of E not happening, we usually put a bar over the top. So that indicates that we want the probability of it not happening. So some theory to begin with. The probability of something happening will always fall between 0 and 1. If you do happen to get 0, then we say it's impossible. It could never happen. There's no chance of it ever happening. And at the other end of the scale, we call it a certain event. It must happen. Doesn't matter what else goes on, that event must happen. And then you have all the probabilities in between. Now, if all the events are equally likely, then our sample space is what we call uniform, spread out nicely. How do you calculate the probability of E? Well, there's the formula. We don't often use the formula because in a lot of cases it's just very intuitive what it's going to be. But technically that's the formula. I mean, what's this mean? Well, what looks like the absolute value, so we're using those symbols, just simply means the number of times the event occurs, so the size of the event space, over the total number of possibilities, so the size of the sample space. Well, before I do that, so back to the coin one, where we said the theoretical probability of tossing the head was a half. Well, number of times E occurs, well, there's 1 head on a coin. Total number of possibilities was 2, because you could have a head or a tail, 1 over 2. So that's what I mean. We don't generally use a formula for that. We just sort of look at it and go, well, intuitively we can see it's 1 out of 2. The complementary event idea, the probability of something not happening must be equal to 1 minus the probability of it happening. And the reason for that, we said probability 1 was a certain event. It must happen. Well, either event happens or it doesn't happen. One of those 2 things must happen. So the 2 probabilities must add up to 1, because it's a certain event that one of those will happen. Well, you play around with that and you get this formula. Probability of it not happening is equal to 1 minus the probability of it happening. And in a lot of cases, it can be easier to work out the probability of something not happening than working out whether it does happen. And then you subtract it to get your answer. So writing up sample spaces, we want to know how many things are in the sample space, so we need to know what's in them. Different ways of doing it. So when you have these, what we call multi-stage experiments, so an event that's happening over and over again, those sorts of things, writing down the sample space can help. So we could create a list, simply writing down every single sample space. Here's an old question. Comes from the 2004 HSC. We've got a game. In this game, a turn involves rolling 2 dice. It's an unusual dice. Instead of going 1 to 6, it goes 0 to 5. The score for each turn is calculated by multiplying the 2 numbers uppermost on the dice. So I write out, okay, well these are all the possibilities then. I could get a 0 and a 0, the score would be 0. All the way up to I could get a 5 and a 5, the score would be 25. So I've listed all the possible outcomes there. The question was, what's the probability of scoring 0 on the first turn? Now a turn is when we roll both. So I have a look at my sample space and I say, well, geez, it's got to end up being 0. How many are there? And I start looking at them and I go, oh look, all of those turn out to be 0. So 11 of them, and there was 36 in total, 11 over 36 is our probability. Well, what's the probability of scoring 16 or more? Again, we just have a look at our sample space. We go, well, there's 16, 20, 20, and 25. So 4 in 36, which simplifies down to be a 1 in 9 chance. Now notice how I write my answer. I don't just simply write 11 on 36, 1 on 9. Remember, your solution is explaining someone. So you want them to know what's 11 on 36. So I'm saying, well, the probability, and in parentheses, the event. Well, the event is that they equal 0. Or in the second one, the event is that it's greater than or equal to 16. So we let them know this is the probability that we're trying to find. Okay, a dot diagram is another way you could do it. A pair of dice, let's do that one. This time regular ones. Probability, they total 3, they total 7. I can draw up like a grid, so one axis is one of the dice, other axes the others, and then you got all these dots. I suppose it's no different to simply writing down 1, 1, 1, 2, and so on. She's sort of got a dot representing. And total 3, well, there you go, that's those 2 there. 2 out of 36, so 1 in 18. Total 7, which is the most common outcome, by the way. And there they are down that diagonal. 6 out of 36, a 1 in 6 chance that they total 7. Probability of totaling at least 3. Now this is where I'm going to use that complementary event idea, because working out probability of 1 or 2 is going to be quicker than working out greater than or equal to 3. Because if I do 3, I've got to work out 3, 4, 5, 6, 7, 8, 9, and so on. Whereas the complementary event, all I've got to do is 1 or 2. So 1 or 2 is a 1 in 36 chance, and that gives me 35 on 36 as the probability. Tree diagrams, probably the most common way we see. So let's do this one. In a raffle, 30 tickets are sold, there's 2 prizes. Probability, someone buying 5 tickets wins exactly 1 prize. So my tree diagram. Start off, the first event, I could either win or lose. On the branch, unless they're equally likely, if they're not equally likely, we tend to write the probability of it happening on the branch. So probability of winning is 5 in 30, losing 25 in 30. We're now going to pull out another ticket. Again, we could win or lose, but the probability's changed because we don't put the ticket back in. Winning now is only 4 on 29 because one of our tickets has been pulled out and won. Losing therefore is 25 on 29. But on the other branch, if I had lost first up, then winning is 5 on 29, losing is 24 on 29. At any stage in your tree diagram, the branches should add up to be 1. Because again, all the probabilities must add up to be 1. I can now see the different outcomes. I've got win, 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 loss, loss, win, and loss, loss. And to calculate the probabilities, we multiply along the branches. So the one we want is probability they win exactly 1 prize. So exactly 1 prize would be the win-loss, and the loss win. I'm going to add those two together. Now, probability, if you find yourself saying the word and, then you multiply. If you find yourself saying the word or, you add. So in this one, I'm saying I could have a win and a loss, so that's why we multiply along the branches, because we had a win and a loss, or I could have a loss and a win, so that's why I'm adding the two probabilities together. I'm saying these are two things that could happen, so I add the probabilities. And we end up with 25 on 87. What's the probability of winning at least one prize? You see that word, at least? There's a trigger to use the complementary event. It usually means it's going to be easier to find the other way of doing it. So at least one prize would be 1 minus the probability of no prizes. So loss. And loss gives us a total there of 9 on 29, because loss was 20 on 29. Okay. There's our quick recap of probability.